Hello folks and welcome back to Skybound on the Ground with Michael Lombard. My name is, oh you guessed it, Michael Lombard. We've been learning a lot about aerodynamics in the past couple lessons. We learned about how wings produce lift, how you can change that amount of lift by varying the angle of attack that the wing is flying at. We learned about ground effect, aircraft stability. And then I left you hanging when I told you about spiral instability, namely that tendency of an airplane, if it gets a wing low, to actually increase its bank angle and the nose gets down and the plane gets in this steepening spiral descent. And what happens often is pilots who don't have any instrument flying experience, if they find themselves in the clouds without any reference to the horizon, they have no way which is up or down, and their body deceives them, and even though they try to maintain their airplane in an upright position, they inevitably get into this downward spiral, and it becomes a graveyard spiral because they end up crashing the plane at the end. Now, of course, a plane that just crashes is going to come to pieces on the ground, but accident investigations have often found that airplanes that have come out of this kind of a situation were actually pulled apart in the air before they even touched the ground. How in the world does that happen? Well, we're going to learn about that in today's lesson because we're going to talk about load factors. And by the way, today's lesson is based on the Pilot's Handbook of Aeronautical Knowledge, Chapter 4, Aerodynamics. We are wrapping up our three-part series on aerodynamics, and then we'll be moving on to more stuff out of that handbook. So how in the world can you pull an airplane apart in mid-air? Load factors. What an airplane feels during maneuvering flight. So in order to understand that, let's take a look at a very simple maneuver, the turn. How in the world does an airplane turn? Well, remember, you have an airplane, if it's flying in straight and level flight, you have this upward force, and that's called lift, and that's what holds the airplane up in the air. Well, the way we turn an airplane, you've seen it done before. You've probably flown in an airplane, commercial airliner. The airplane banks, and what happens is that lift now gets redirected. It's still acting straight up through the wing, but now the wing is pointing sideways. And so now, if you broke it down into components, you would discover that the lift has a horizontal component, and that is exactly how an airplane is able to turn, because of this horizontal component of lift pulling it around the corner. Alright, so now we know how an airplane turns. Can we figure out how we can change the rate at which it turns, how fast it comes around full circle? Well, you're probably thinking all you have to do is steepen the bank angle, and you're right. Steepening the bank angle will help the airplane increase its rate of turn. It'll come around a lot quicker. But airspeed also has a role to play. If you're flying at a faster airspeed, it's actually going to take you longer to make that circle than if you're flying at a lower airspeed. And it also affects the radius of turn, how much room it takes you to make that circle. So if you're flying along at 50 knots, and you would be able to make your circle in that amount of distance, whereas if you're flying around at maybe 100 knots, it's going to take you a lot more space to turn around in. And you can think of it as if you're driving a car out on a big flat surface. Going at 100 miles per hour, you're going to take a lot more area to make a complete circle than if you're driving at 5 miles per hour. You can just turn around in a really tight space. So that's this has important real-world applications, because say you're out flying, doing something you're not supposed to be doing. Why do we use these kinds of examples? Okay, you are flying up a canyon, and this is a bad idea, but you decided you were going to go do it anyway because you thought this was the right canyon. And you're flying this pretty little river down in the bottom, and those are the canyon walls, by the way. And suddenly you discover, oh no, or look at that, there's a lovely waterfall at the end. And uh-oh, that also means there's a canyon wall. And this is the wrong canyon, there's a end to it. This canyon doesn't continue. And so what do? We have to, there's no way we can climb out because we're too low now. And so what you end up doing is you try to turn around. But you came screaming in at like 150 knots, and so your turn radius is going to be really wide, and you end up smashing into the wall over there. Well, what should we have done? Well, we shouldn't have gotten ourselves in this situation in the first place. But now that we're here, what we should have done is slowed down the airplane as much as we could, and then started our turn, and we would have had a much tighter turn radius, and perhaps we would have been able to turn around and get out the other side again. So that's why it's important to realize how your airspeed and your bank angle affect the rate of turn and the radius of turn. Okay, so now if you were paying attention when I drew this up here, and that component and the lift when we bent it over to the side by banking the airplane, you probably realize that we now have a situation that was similar to when we put an airplane in a climb. Because lift is no longer doing all of its job of holding the airplane up in the air. The airplane still weighs, let's say, 3,000 pounds. Actually, I'm going to write that on the other side. And say the wings are still producing 3,000 pounds of lift, but they're not producing that all in the upper direction, whereas the weight is still acting straight down towards the bottom of the earth, towards the center of the earth. So we have a problem here. What do? We need to increase the angle of attack that the airplane is flying at. So pull back on the yoke, and that's going to increase the angle of attack. Then we'll produce a little bit more lift on the wings. And then you'll have the equal amount of lift that is going upward. The vertical component will once again equal this downward force of 3,000 pounds. And so you're going to increase the angle of attack, fly the airplane at a little bit higher pitch angle, and because you're going to increase drag that way, you're going to also have to push forward the throttle a little bit and up your thrust there. Okay, so that is how we are able to maintain our altitude while we are turning. And that's because we increase the amount of lift that the wing is producing. Now, I remember when I was a kid, I used to think that if I was flying in an airliner, I would be able to dangle something on a string and be able to figure out if the airplane was in a bank or not without having to look out the window based on whether this object would deflect to one side or the other. Well, it never seemed to work, and I couldn't figure out why until I was introduced to this diagram. Because you see over here, there is another force at work. It's not just the horizontal component of lift and gravity, and so because I thought, oh well, gravity is acting straight down, so the object should just dangle towards where the Earth is. There's another force at work, and we've all felt that force when we've been driving along. Maybe our friend is driving, and he comes up to the corner, and he takes that corner really quickly, just cranks around the wheel, and what happens to us? We get plastered against the side of the car door. Very uncomfortable feeling, right? Well, that is what causes that is your inertia. Your body wants to keep on going the same direction it was going before your friend so abruptly yanked on the wheel. And the airplane is feeling the exact same thing when you put it into a bank. We call this centrifugal force. And so that is working in the opposite direction of the horizontal component of lift. So centrifugal force is working out that way. And when you add these two together, you find out that the resulting force is actually just straight down through the airplane. And so you're going to be sitting here, and that object is just dangling straight down in relation to how you're sitting. You could actually even pour yourself a cup of, hot soy milk or something, and it would fall right directly into your cup. So you wouldn't feel as if you're being pushed to one side or the other because the force is just straight down. These two forces are balanced, and we call this coordinated flight. Now, there are ways that if the pilot is not doing his job right, you might feel as if you're being squished to one side of the airplane, and that would be if the pilot tries to turn the airplane by just using the rudder. So he's going to yaw the nose over to the side, but that's a problem because he doesn't really have that component of lift, that horizontal component of lift pulling the airplane around the corner, and because it's flying in the air and it's free, there's nothing to grab onto, it's just going to kind of fly sideways. It's going to be skidding. We call this skidding, a skidding turn. And you're going to feel as if you're plastered up against the outside of the turn there, just like in the car. Well, that's a skidding turn. There's the opposite. If the airplane is banked, but then you kind of use the rudder and you don't let the nose come around. So now you have this horizontal component of lift that is trying to pull the airplane around the turn, but you're not letting the nose come around, you're not letting the airplane actually turn. And so the airplane is just going to be kind of slipping to that side, but not actually really doing a turn either. And you're actually going to feel as if you're falling to that side. It's also an uncomfortable feeling, and that is not coordinated flight, folks. We want to keep things balanced so that you can sit straight up in your seat and you won't feel as if you're being jostled to one side or the other. Now, you also will notice, and we kind of alluded to this, that, okay, the airplane weighs 3,000 pounds, but it's actually feeling more weight than that. And this is where load factor comes in. So the upward amount that we're having to support, is 3,000 pounds, but the total amount of lift that the wing is producing is actually more than that. And when you add up the centrifugal force and the weight of the airplane, you realize that the wings are having to produce something like, 3,600 pounds. That's how much the airplane feels like it's weighing. And this is called load factor. And you've heard about this, it's called, in a different term, you've probably heard about G-forces. This is what fighter pilots experience when they're, pulling a loop or something like that. It's how many times the force of gravity you are experiencing. And G-forces are actually very much related to your bank angle. Let's take a look at it. Okay, so if you're at 1 G, you're actually going to be in straight and level flight. Let's put you into a 45-degree bank angle. You're actually going to be pulling about 1.4 Gs. Bump it up to 60 degrees, and you're going to be pulling 2 Gs. That's a good round number to keep in mind. 60-degree bank angle equals 2 times the force of gravity. You're going to run into that probably on a test or something. Now, things start ramping up even more. If you increase your bank angle from just 60 to 70 degrees, just 10 degrees more, you increase your load all the way up to 3 Gs. And so an airplane that normally weighs 3,000 pounds in that turn is experiencing a total force of 9,000 pounds, three times the force of gravity is at work on this plane. And it gets even better as you increase the bank angle. Let's say we go up to 80 degrees. Now we're all the way up past 5.5, and it just keeps on going up from there. Wow, yeah, can you even stand that? Well, the question is, can your airplane even stand that? Airplanes are actually designed with a limit. There's only so much that an airplane can take before you start bending things. And a normal category airplane will be about 3.8 times the force of gravity, 3.8 Gs, and that is called our limit load. Excuse my messy handwriting. 3.8 Gs is the positive limit load. You can also pull negative or experience negative Gs when you push over. That's a very uncomfortable feeling because you go past weightless and then everything comes up. Maybe even your breakfast. But the negative load limit that the airplane is, normal category airplanes are certified to, is minus 1.52 Gs. That's the negative direction. So we want to make sure that we're careful when we're flying our airplane, because if we exceed 3.8 Gs, we're going to start bending stuff. And how does that happen? You can put loads on the airplane. We've already seen how you can put loads on the airplane by putting it into a steep bank angle. When you put it into a 60-degree bank, you put on 2 Gs. When you put it into a 70-degree bank, you're putting on 3 Gs, and that's getting pretty close to 3.8. So you got to be careful how steeply you bank your airplane. There's other ways that you can also put loads on the airplane, and that's just wild maneuvering. Just anytime you abruptly change the direction of flight, you're going to put loads on the airplane because the airplane has inertia, wants to go the other direction, and now you're stressing it, you're putting these loads on it. And so that's what you got to be careful for that you don't exceed those limit loads. Now, how does this work with stalls? Because there's an interesting phenomena that occurs when you're flying at higher loads, at higher load factors. The stall speed of an airplane actually increases. How does that work? Well, let's quickly review stalls here. Remember, an airplane wing normally has the air that's flowing over it. It's flowing over nicely and smoothly, and that's how we're producing lift. But if we increase the angle of attack to the point where the air that's coming over is no longer able to flow smoothly, and instead it eddies and burbles and backfills and creates all this turbulence, basically lift is starting to be destroyed here. It's not completely destroyed, but it's largely destroyed, and the wing is said to be in a stalled condition. It has nothing to do with the state of your engine, but it has everything to do with the state of the airflow of your wing. It's an aerodynamic condition. So when a wing stalls, it actually doesn't have any more load on it, but before it stalls, okay, I'm getting ahead of myself here. But so airplanes, when you stall the airplane, you have exceeded that critical angle of attack. Now remember, when we're in a turn, we have the airplane banked, and we don't have all that lift working upwards anymore, so we have to increase the angle of attack in order to produce more lift, and the airplane is supporting much more weight now, and so you're flying the wing at a much higher angle of attack. If you have the bank angle so much that that angle of attack is exceeded, you're going to stall the airplane. Even though perhaps you were flying at 100 knots, you put the airplane in such a steep bank that in order to maintain level flight, you actually stalled the plane. That's how stall speed increases when you increase the load factor. And there's actually a formula for it. When you increase the load factor, the stall speed increases by the square root of the load factor. So basically what that means is if you are pulling 4 Gs, the square root of 4 is 2, so an airplane that normally stalls at 65 knots is now going to stall at 130 knots. So you might be in this 75-degree bank, just hauling that airplane around, and you're pulling 4 Gs. Put just a little bit more load on there by increasing the bank maybe over to 80 degrees, if you could even do that. Well, you actually can, but it's really bad, once again. And you stall the airplane because it just can't support all that load anymore. But if you were paying attention to the number I wrote on the board earlier on, you might have a problem already because 3.8 is the limit load for normal category airplanes, and we were just pulling 4 Gs, so we've already started bending things. That's not a good thing. So in order to keep from bending our airplane, we need to understand another diagram. We're going to take a look at the VG diagram. The VG diagram is called VG diagram because it plots velocity, which is our V, against G's, which is our load factor. So velocity is our airspeed, and this is the amount of G's that we're pulling. So an airplane normally stalls, let's say this airplane normally stalls at 65 knots. If the airplane is in straight and level flight and you go below 65 knots, you're going to exceed the angle of attack trying to maintain lift, and the airplane will just stall. If you are in a straight and level flight at 65 knots and you put it in a turn, you're going to exceed your load limit. You're going to exceed the amount of load that the wings can support at that speed, because you're going to have to increase your angle of attack in order to maintain your altitude. And the airplane will stall if you try to put more load on it. So 65 knots right here. This is stall speed at 1 G. And then we have 2 Gs. Stall speed at 2 Gs is about 91 knots. I did the math beforehand. There's a formula for that, but we won't go into that right now. And then we want to make sure that our airplane doesn't get bent while we're maneuvering it, and so we want to figure out what the maximum airspeed is that we can bring it up to stall without bending it. So 3.8 G's is the load that we don't want to exceed, right? So that's right up here. So 3.8. So right up there ends up being about 126 knots for this airplane. Take it up to 4 G's, and if you fly the airplane at 130 knots and you pull 4 G's, you're going to stress the airplane too much. So this point over here, this is called design maneuvering speed, and this is a very important number because what it basically means is that you can do whatever kind of maneuvering you want below this airspeed. You can stall the airplane, you can pull it out, you can just wildly maneuver it around, and it's going to stall before it reaches 3.8 G's. And when you stall an airplane, you relieve all the load off the wings. The airplane is going to start falling, so that's another problem in itself. But you're not going to bend your airplane, which is a good thing. It kind of acts like a safety valve. But if you start flying the airplane up past this speed over here, up past 126 knots, now you don't necessarily have a guarantee that you're not going to bend your airplane if you're maneuvering your plane wildly about. And so you could be flying up at 130 knots, and you put the airplane into a steep bank, and you pull it around and yank and bank, and you bring it up to 4.5 G's or something, and now you are in this damage range, and you're putting damage on the airplane. Not a good thing. There's also a point where it's actually going to experience failure. Fail you. Anyway, and that is definitely a place you don't want to go either. There's also a speed over here where, let's say that's 150 knots. Remember how introducing a gust, if you have a gust that moves the airplane around suddenly, that's also going to put loads on the airplane. And so if you're flying along at 150 miles per hour, 150 knots, and a sudden gust hits you, we've all experienced turbulence, some sudden gust like turbulence hits you, that can also shoot the airplane right up here into the damage range. And so that is why you only fly in this caution range when the air is completely smooth, when there's nothing more than very slight turbulence. And we call this speed over here maximum structural cruising speed, because anything above here, any type of turbulence that is, any type of moderate turbulence is going to bend your airplane because it's going to put too much loads on it. There's a speed over here, let's put it right there, that if you go faster than that, we never go faster than that. It's called the never exceed speed. And that's because bad things start happening to the airplane. You could have structural failures. Anyway, things start flying off. Who knows what. So we don't go past the never exceed speed. That's called red line airspeed. So the takeaway from this is that we need to make sure we know what design speed, what maneuvering speed is for the airplane we're flying. Whoops, maneuvering. And you'll actually see this referred to as VA. There's all these different V speeds, V1, V2, VS, VA. And that's, so maneuvering speed, it'll be different for each airplane, but this is the speed at which, as long as you're flying below this speed, you can do whatever you like to the airplane in terms of maneuvering it, and it won't exceed 3.8 G's. It'll stall before it ever gets to that point. Flying above that speed and you do some wild maneuvering, you're going to put too many loads, you're going to put too much load on the airplane, and it's going to get bent or even come apart. And that is exactly how our pilot, who found himself in the clouds, out of control, pulled his plane apart. That's exactly how it happens. because the airplane ends up getting in this spiral dive. It gets going too fast. He's wildly pulling on the controls because he's trying to get the airplane back to level, but he really doesn't know what level is, and so he ends up pulling the airplane apart in the air because he puts too much load on the airplane. And that is what happens. So, what's the moral of the story? Number one, don't go flying in the clouds unless you have an instrument rating and are properly trained in current and all that stuff. It is safe once you get the training. But number two is make sure when you're doing any type of maneuvering aside from just regular turns, climbs, descents, if you're going to be doing any type of other maneuvering, make sure you are flying your airplane below maneuvering speed, so that if perchance you get yourself into a little bit too much of a bank and you're pulling too many G's, at least your airplane will stall before you bend it. You'll have to figure out how you can recover from your stall, but make sure you're flying below maneuvering speed. Okay, so we have learned a lot, and to kind of tie things off for today, we're going to go into props. We're going to talk about how propellers work and these wonderful things that pull our airplane through the sky. Now, if you look at the side of a propeller, you'll actually realize that it looks like something very familiar. So let's draw a propeller hub here. So here's the front of the airplane, here's the propeller hub, and here is the propeller. And what does that look like? That looks like a wing, doesn't it? And actually, that's basically what it is. It's like a miniature wing. And we call it an airfoil because it produces, airfoils are some type of surface that produces an aerodynamic force when it's moving through the air. And so this, just like a wing, it moves around and it has this angle of attack, has the leading edge, the trailing edge, and so it has an angle of attack. The propeller blade is set at an angle. We call that blade angle. And for airplanes that we're going to be flying, most of them are, for the training airplanes, this blade angle is going to be fixed. It's just going to be one propeller blade angle. You can change the speed at which the propeller is turning, but you can't change that angle. There are fancier airplanes, variable pitch props, where you can actually change that angle and it'll actually regulate itself automatically while you're flying. But for the plane that we're flying, that most likely you'll be flying, it's going to be just a fixed pitch propeller. Now you can see the propeller is moving through the air, and it acts just kind of like a wing. And so you have the angle of attack, you have air flowing over, and you basically get this rearward force going on, and also the low pressure, the high pressure on that side, all that lovely wing stuff going on. Now you'll notice also, as we're talking about propeller design, that propellers are kind of twisted a little bit, and the reason, well, that's really a bad drawing. Let me do that again. So they're twisted a little bit, and the reason you do that is because the outboard part of the wing is actually moving a lot faster than the inboard part. Even though the whole thing is moving together, you can imagine it as if you're running around a track, and you're running in the outside lane, whereas the guy that you're trying to keep up with is running on the very inside lane, and so you're having to run a lot faster to keep up with the guy. You both finished at the exact same spot, but you ran a lot faster, so it's the same thing with the tip of the propeller. And so because of that, if this propeller tip is moving a lot faster than the inboard tip of the propeller, than the inboard part of the propeller, then you're going to be producing a lot more force on the outside. So they actually twist it so that it produces equal force along the range of the propeller. Okay, so now we have seen how the propeller design is. Oh yeah, I also need to mention that when you have a fixed pitch propeller, it's not as efficient as those fancy variable pitch propellers, because it's only going to be efficient at one flight regime, one airspeed that you're going to be flying at. And it's kind of like riding a one-gear bicycle. It's going to be a lot harder work when you're riding uphill, or if you're going downhill really fast, you're not going to be able to keep up. it's kind of the same principle with the fixed pitch propeller. It's going to be optimized for a certain airspeed, and every other airspeed that you're going to fly at, it's not going to be as efficient. That's just the reality of simple things. But let's take a look at something that we need to know about propellers. And this is the downside of flying propeller aircraft, and that is something called left turning tendency. So let me grab my handy dandy propeller plane here. I went downstairs and found my Lego component so I can illustrate something to you in terms of propellers. So anyway, I'm having a lot of fun spinning this right here. This is our airplane. This is our propeller airplane. And in certain flight regimes, we're going to talk about high angles of attack, high power. Propeller planes have a tendency to turn to the left all by themselves. That's something we have to be careful about, and we have to pay attention to. And why is that? Well, you're going to be asked this a lot, and you're going to have to be aware of it. There are 4 factors that affect an airplane's left-turning tendency when you're flying a propeller airplane. And let me just write out these 4 factors. The first factor is torque. Second factor is slipstream effect. And then you have, gyroscopic effect. And then finally, P factor. Okay, so torque. You got this propeller out front, and the propeller is, okay, first of all, let's get things straight. Most airplanes that are built in the US, the propeller turns clockwise when viewed from the pilot's seat, just so we know that. Okay, so the propeller is turning clockwise. You've got this thing twisting around, and what's that going to want to do to the airplane? That's going to want to twist the airplane the other way. And so if you look at it from behind, it's going to have this rolling moment to the side. That's the torque of the airplane at work. Designers try to compensate for this, but usually it'll only be compensated for most effectively when the airplane has reached cruising flight and it's going at full speed ahead. But when you're at high angles of attack and low airspeeds, it's going to have this left rolling moment. Okay, so that's torque, and that's affected by how strong the engine is, how compared to how small or big the airplane is, and how big your propeller is. So torque has this tendency to roll the airplane to the left. Slipstream effect, because the propeller is rotating to the right like this, it makes this corkscrew slipstream of air that circulates around the airplane, and it comes and it hits the tail of the airplane. And remember the weather vane effect, it'll actually tend to move the airplane to the left again. And it also has a little bit of a right rolling moment, so that kind of cancels out some of the torque effect, but not quite as much. Okay, so that's slipstream. And then gyroscopic effect. This is an interesting one. And I don't know if you've ever tried this, but I couldn't get a bicycle wheel on to fit in the frame here, but I'm just going to illustrate this with this handy-dandy paper plate. But you may have tried this before, where you hold a bicycle wheel and you spin it up and you're able to hold it with some handles. And what happens when you try to move it? Well, first of all, you notice that it's really rigid, and that's because it has this gyroscopic property. When you spin something and you make this spinning disc, it's going to want to stay rigid in that position despite whatever forces you put on it. Well, the other thing you probably notice is if you did manage to put some force into it, you tried to twist it this way, what happened is the bicycle wheel actually ended up twisting in a way you didn't expect. And that's because the force comes in and it comes out again 90 degrees away from the direction that you put it in and the direction that the gyroscope is rotating. So what that basically means for us pilots is that if you had this tail dragger, this was important in the tail dragger flying days, if you had a tail dragger and you're going down the runway and you're about ready to take off, so you're going to lift up the tail, well, the propeller spinning is basically, the propeller is a big old gyroscope right there. And so because you're putting this force in, it comes out 90 degrees away and in the direction of the propeller turning, and so it actually twists the airplane off to the side. And that could be very disturbing for a pilot who was not expecting it. So he raised up the tail so that he can get in get the airplane ready to fly. And when he did that, if he did that too quickly, the plane would just veer off to the left of the runway. Well, you and I are probably going to be flying tricycle gear airplanes, and so that's not going to be much of a consideration for us. But hey, when we lift up the nose, you'll have a little bit of a right turning tendency. Maybe not much, but it will have a little bit of effect. So there's all these things that are going on, and finally there's P factor. And no, this is not a physiological factor of being in the airplane too long without a bathroom break. No, P factor has to do with prop loading. And take a look at this propeller here once again. Now, when the airplane is in high angles of attack, remember it's going to be flying through the air like this. And this is what you're going to be encountering when you're taking off the airplane. The airplane's going to be at low air speeds, high angles of attack as you're trying to accelerate and climb. Now, notice what the propeller looks like from the top. If the airplane is just flying at a normal angle of attack, you can see that the ascending and the descending prop both are taking equal bites out of the air. They have the equal amount of surface area exposed to the air. But notice what happens when we pitch the airplane up and increase the angle of attack. Now, the airplane, remember, looking at it from the top, so it's going to kind of move towards you as we pitch the airplane up. So look what happens. Oh, interesting. So the ascending propeller on this side is actually taking a lot smaller bite out of the air. It has a lot less surface area exposed, and you can see the descending propeller is taking a lot bigger bite out of the air as it descends. And so what happens is this propeller is actually making a lot more aerodynamic force than the propeller on the other side. And what that translates into is the left turning tendency. So looking at the airplane from the top again, this is our airplane. Okay, so the descending propeller on the right side is producing more force than the one on the left side, and so once again you have this force that's turning the airplane to the side, the left turning tendency. So these are the four factors that are at work. And honestly, I do not think about all four of them when I'm flying the airplane and taking off, or flying, at high angles of attack, low air speeds, whatever. All I do is I look out the window and see if the airplane is starting to drift off to the left, and if it is, I push right rudder. I know about these factors, but because they're always changing, there's no way you can calculate in your mind, oh, gyroscopic effect is going to be affecting me right now, and not as much as P factor, blah blah blah. No, you just are aware of the general principles and know when it's going to affect you the most, and then you just fly the airplane, and that's why we take lessons. But it is important to know these factors involved. But then, when you know the general principles, you can go out and fly the airplane. And hey, I really want to actually go and start flying, and I bet you do too. And next chapter is really exciting because we're going to start learning about the flight controls, how we can actually maneuver our plane in the air, use our controls to do what we want to do in the flying. But that's going to have to wait until next time on Skybound on the Ground.